Projector 2 obviously had a very good weekend. Right, so let's just go back to the final couple of pages about the spectrum of synchrotron electrons that we were covering on Friday. Now, what I got to towards the end of Friday is this point here. The idea is that if you take a single electron, just do a thought experiment with a single electron on the end of a piece of string being whirled around at relativistic speed. If you're looking at that, then the observer will see a little flash of radiation every time the electron goes over the top of the circle, as it spins in a very, very narrow emission cone. Then the analysis that we did was to take a Fourier transform of that set of pulses, and you find that a single electron, or a population of electrons, which emit at a single frequency, a population of electrons which emit synchrotron radiation, then they will emit radiation in quite a narrow range of frequencies, okay, which is centered at gamma cubed times their gyro frequency. So gamma cubed times the frequency which they're orbiting, and most of the energy comes out within a factor of 2 of this. So this is a very, very narrow range of frequencies compared with the many orders of magnitude of electron energies that are present in the population. And I did, as I said on Friday, I did that little trick of doing this by convolution theorem in the Fourier domain, and a couple of people asked me for a reference to the full calculation, which is in here. This is a 1960s, lovely 1960s theory book by Prokolchik. And I think I might scan this in, but you go through several pages of this. And so what you're doing here, essentially you're doing the same thing, but you're taking that pulse shape, working out the precise pulse shape, and then Fourier transforming, and you get the precise shape of the Fourier transform. Right, okay, but the thing to remember here, the important thing about physics here, is that this range of radio frequencies, for example, that an individual electron energy will radiate, is small compared with the large range of energies in the population as a whole. And that's the thing we want to deal with next. So if I just get my last couple of pages at the very end of lecture 2, let's just look over that, and then we'll see basically the circle then ends up completed and you get the spectrum that you observe from these sources. Right, so this is the end of lecture 3. Right, so this section is the spectrum from a population of electrons. And the idea here again is to use convolution. So what I'm showing here on this plot is this is the flux per unit frequency against frequency of an individual electron at a particular energy. And if you convolve that with the electron energy population, E against N of E, so there's a large range of electron energies going to arbitrarily large or arbitrarily small energies. And as we discussed previously, we imagine that if first order shock diffusive acceleration is the mechanism, then we'll find N of E is proportional to something like E to the -2 in the simple, most easy to calculate case. So if you convolve the two of those, you'll end up with the synchrotron spectrum that you would expect from the whole population. So we're back now in mu against F mu space. And as you might expect intuitively, what's going to happen is because this convolution kernel is very narrow compared with the breadth of the energies in the population, you would expect to get a power law, but the power law slope here may not necessarily be the same. Right? So You can imagine, if you like, to take it to the extreme, in the limit, any individual electron it emits at its own energy, at a delta function, and then a delta function involved with the electron energy spectrum will give you another spectrum. Similarly, got power law. The power law index is going to be different. So we consider this narrow single electron spectrum. The broad population electron energy distribution just for the sake of the algebra right now, I'll call that spectral index minus k. Okay, right. Remember from Friday, the total power coming out of a single electron power as a function of the electron's energy. Okay, so this is the electron's energy at one instant. That's its kinetic energy as it was around in a circle. The power is the synchrotron radio emission rate that it has. And then, sorry, that's proportional to E squared. E squared. Right, remember that's the gamma squared in the derivation we get on Friday. Okay, and then also remember for a single electron, there's a relationship between the electron's total energy and the characteristic frequency at which it emits. And so that's the characteristic frequency here. This is in a constant magnetic field. This is a function of the total kinetic energy of the electron at some point. And really, this is actually pretty simple, because all you just need to do is change the variables here. So dE will be proportional to mu to the minus 1/2. Mu, just differentiating that. And then let's consider, right, what is this flux per unit frequency as a function of frequency made up of? Well, F nu dnu will be the power emitted by a single electron times the number density of the electrons as a function of energy, d energy, where there are going to be two corresponding limits. So you could think of this almost in the same way as you might take the optical spectrum, when you look at the spectrum of an object, you could write it out in terms of wavelength, and you'll say, okay, what's the total amount of power emitted between 500 nanometers and 501 nanometers? That's got to be the same total power that's emitted between the two corresponding frequencies, how many terahertz, petahertz is 500 nanometers. So that the two corresponding frequency ends of the interval are the same, contain the same amount of power as the two corresponding ends in the electron energy. Right? So this is the range of observed synchrotron frequency emission, and these are the two corresponding ends of the energy bin. Right? So the total flux emitted has to be equal to the total flux emitted by the electrons that are in that corresponding range. So this is that's just a change of variable. So that, folding in my b squared, e squared from above, that then must go as b squared, e squared, and then e to the minus k, the energy. So that's going to scale as e to the 2 minus k, the energy, and then for our variable changing explicitly, that will scale as mu to the 1 minus k over 2 mu. So remember, we talked about our spectral index in the sense that the synchrotron flux is proportional to mu to the minus alpha. Okay, I'll be careful here to say, right, that's a proportional sign and that's a Greek alpha. So this means alpha is k minus 1 over 2. So that's the spectral index of the synchrotron radiation. Okay, that's the spectral index in the radio frequency observed audio. And that k is the energy index. So this is, in our case, for the standard shock acceleration, simple derivation, that's e to the minus 2. So k is minus 2. That gives you alpha of 0.5. And that is the shallow, standard, optically thin synchrotron spectrum that we see. So in this region here of the spectrum that I showed you for different types of radio sources. So now, it's definitely the case that minus 0.5 is essentially the shallowest that you see. Now, in practice, what happens is that you tend to see this spectrum starting to get steeper and steeper, and it tails off very quickly at high frequencies, and it also rises very quickly at low frequencies. And those two things we'll talk about as the bulk of lecture 4, but before we'll formally get into lecture 4 right now. But at this point, what you're seeing here is, what you're seeing at that standard spectral index is you're seeing, underlying this, you infer that there's a large population of energies, and the electrons in the population have got a parallel index in their energies, and you're seeing synchrotron emission coming out of them. Each individual electron energy emits synchrotron at some particular characteristic frequency. That's the message to take home from this bit. Right. Now I can get on to actually lecture 4. If it will connect. I'm not asking for a updates. Ta-da, okay. Right, okay, so what we're looking at here today is the ends of this spectrum. Right? So the sharp rise at the low frequencies is synchrotron self-absorption, and then the tail off at higher energies is an indication, and it's largely believed in extragalactic radio sources, this is something that we can look at quite clearly, that the population itself is aging, and that gives us a handle on the age of the population. Might sound trivial to say, but very interesting that you can age date objects out at cosmological distances. Right, so just to recap very quickly, this is what we've just been discussing. This spectral index here, the shallow ones here tend to be maybe about 0.5 at their shallowest. Sometimes you can see them getting a bit steeper, and then there's quite an abrupt sharpening and steepening of the spectrum at the very high end here in many cases. Now, the low frequency end also, you see it rising. So often in a radio source, there's maybe 3 or 4 orders of magnitude in synchrotron frequency with a rise at the bottom and a fall off then at the top. Okay, so the first thing we want to do now is to look at the low frequency rising part of the spectrum. And what's happening here, in simple terms, I can probably fall back on what we talked about optically thin versus optically thick spectra earlier on in the lecture course. It's to do with scattering of the synchrotron photons within the radio source. Okay? Now, remember we discussed when we were talking about optical spectra, the idea that the surface of the sun, for example, has an optically thick plasma. You don't see very far into it. Essentially, most of the light that you see when you look at the sun comes from an average optical depth of about 1 distance of about 300 odd kilometers. So when you're looking at the surface of the sun, you basically just about only see the surface. Now, if you talk about synchrotron photons, so now we're talking about gigahertz frequency or maybe megahertz frequency radio waves here, but put that thought to one side and just think of an individual synchrotron photon. That's propagating through the plasma in the radio source, and the scattering mean-free path is going to vary with the photon energy. Basically then what that means is that as you go to lower and lower and lower radio frequencies, you see shallower and shallower and shallower distances into the source. So at very, very low frequencies, basically you only see the outside shell of the cocoon plasma. Whereas at high frequencies, as we demonstrated in our falling synchrotron spectrum, you basically see it all the way implicit in that variation that I just did, was at any time a synchrotron photon is emitted by an electron in the plasma, it escapes the source. So the calculation we have to do now is, right, what's the situation if it's optically thick? What's the situation if there is scattering along line of sight? And also that scattering depends on the photon energy. Now, once again, there is a long calculation that you can do to do this in detail, but to give you a little bit of physical intuition of this, and especially to tie in with the thermodynamics, there's a nice little calculation you can do. And that's what we'll start off with here. Okay, make sure you write this in your own handwritten notes. And there's no evidence that I ran over by 10 minutes at the end of last lecture. We'll always start right to 4 now. So low energy cutoff in synchrotron spectra. So this phenomenon is known as synchrotron self-absorption. So self-absorption because the photons are being emitted by synchrotron electrons, and then they're also being absorbed by synchrotron electrons before they escape the plasma. Basically, it's very easy to think of this as the optical thick case. Now, if you had a system where you could write down the rate of transfer equation and assert local thermodynamic equilibrium at any point, and that's what we do when we say that d mu over d kappa term is linear in the rate of transfer equation. The thermodynamic underlying assumption there is that there's local thermodynamic equilibrium, and we do not have this in relativistic plasma. So what we do is we use an effective temperature for any particular electron energy. So what we're doing is we're saying we've got a large population of relativistic energy, of relativistic electrons with a power law distribution in energies. But what we'll do is we'll assign an effective temperature to each energy. It's not a thermal equilibrium situation, it's not a common temperature for everything, but you can assign a temperature to each particular energy of particles in the population. Right, so if you remember, for a fully relativistic fluid, the total energy is 3 times the pressure. Remember you did that in do you remember you did that in second year stat mech? Yeah? So if it's relativistic fluid, it's a photon gas, U is 3p. So you simply take that, and then you say, oh, well, that must mean that for any particular particle, I can write Kb and say there's some effective temperature, which is 1/3 gamma. If I'm saying that my fluid is made up of electrons, 1/3 gamma mc squared. So that's all you're doing, saying it's fully relativistic, so U is 3p, And then by equipartition you can say that the KT term must be 1/3 of that. Okay, so if you want a little bit more discussion of that, that's in long air in the new single volume long air, that's page 217. Right, so, 4 particles with some energy with some energy, synchrotron emission occurs at a frequency such that E is proportional to mu to the 1/2. Okay, we're restating that very rapidly after running it this halfway down the board. The idea being that that was in the previous lecture, so this is a recap of it. Okay, so now that is proportional to K times thickness times the effective temperature. Right. So we've asserted up here that we can assign an effective temperature to any particular particle, and then that gamma mc squared is the particle's energy. So that means that the frequency with the sharp peak frequency at which any electron emits in synchrotron is associated with a particular temperature. Now I think you can probably guess what I'm going to do now. What I'm going to do now is I'm going to go back to the Planck brightness formula and say, okay, if I've got a plasma at a certain particular temperature, and I'm just zooming in on one very narrow interval in the Planck frequency distribution, and say, okay, ignore what's happening with the electrons at other energies, but what's the brightness that a population at this temperature, at this frequency, will give you? And so if you just zoom into that little bit of phase space, you still get the same brightness. Right, that's the trick. Each point in your black body, each point in your brightness spectrum will get the frequency will correspond to some particular electron energy because it corresponds to the frequency that the electrons of that energy are radiating. And then the other thing I'll put in to simplify this, because we're always in the Bragg-Jeans limit here, and that's what the electrons being relativistic. In the Bragg-Jeans limit, the black body brightness formula is 2 kT mu squared over c squared. So use our t scales as mu to the 1/2, and you get that the brightness. So now I'm using I to be pedantic because it's not black body anymore. It is proportional to mu to the 5/2. Okay. And that's a result which is what you observe when you look at these sources. If I just switch back to the examples on the this steeply rising part here usually has a nice power law rising at the usual power voltage. And that's the evidence that we're looking at our synchrotron synchrotron emitting plasma lump, and we're seeing it in the optically thick regime until the spectra goes up the spectra goes up at 502. Right, okay. Now, what happens at the high frequency end of the spectrum? So for this, we're going to do a calculation looking at the radiative losses of the electrons in this plasma. We've talked an awful lot before about the total energy stored in the plasma. Well, yeah, the plasma is radiating as it goes. We see these things at radio wavelengths, so that's where that energy is coming from. And ultimately, then that must disappear, and the electrons, the highest energy electrons, disappear out of the population. Now, there's a little caveat that I'll put in here right at the start of this discussion, which is to say that, well, yeah, of course, you do expect that there should be some natural upper limit anyway, if you think about our discussion of shock acceleration. When we talked about shock acceleration previously, we had as part of that the idea that there's always a probability that the electron will be swept away out of the region of the shock. Okay, now fold that in with another thing that's always going to happen with electrons in a magnetic field. So this is just A-level stuff, but with the gamma thrown in to indicate relativistic energies. The radius of an electron's orbit goes like gamma mv over ev. So the radius of the orbit of the electron in a fixed magnetic field grows as the electron gains energy. And one thing that you see, and it's very neat, you can see this when you look at full numerical simulations of particles crossing back and forth across the shock. Each time the particle gets a little energy increase as it goes across the shock, the radius of its orbit in the magnetic field gets bigger, progressively larger and larger and larger and larger. And that radius scales linearly with energy, though. It's just got one gamma in it. So what will happen if you imagine that your particle being accelerated by the shock from a supernova, at some point you'll hit the stage where the radius of your orbit is a parsec or a couple of parsecs, something like thereabouts, and then it's actually the same size as the supernova elements. So there's a natural cutoff at which shock acceleration ceases to work when the gyro radius of the electrons equals the size of the region that's doing the acceleration. And we're pretty secure nowadays in our understanding here in that that's the point. There's a little change in the shape of the electron energy spectrum as you get to about 10 to the 15. And that's where shock acceleration in supernova remnants runs out within a galaxy. And to get to energies higher than that, we believe you need these particles to be accelerated in larger still shocks. And that's where the argument that the very highest energy particles are coming from extragalactic objects, that's where that comes from. And so by the time you want to get up to 10 to the 19 or 10 to the 20 eV, this size starts becoming tens of kiloparsecs. And you reach your argument that to get the very highest energy particles, you must be accelerating on very large scale structures, whether big shocks in the, in the largest size quasars and other active galaxies that you see nearby. However, that's a little bit of an aside. What I want to talk about primarily in this next section is just the idea that the radiation of the electrons is a cooling mechanism, and that's how the energy of the plasma itself ends up being dissipated, and we can use that to date the plasma in any given object. Right, so let's say this is section 4.2. Call this high frequency cutoff. And this technique is known as spectral aging. You know, you can think of it, you can think of an analogy here, it's a bit like radiocarbon dating. When I say spectral aging like this, I'm talking about as a technique that astronomers use to work out the age of a given lump of plasma from which they have this spectrum. So remember previously we had our result we've had several times now. So we get 4 over 3 sigma T, you see magnetic field strength, magnetic field energy density, and then V over C squared and gamma squared. So that's the power emitted by an individual synchrotron electron. So if you have a population of electrons, then at any energy, you can write that as minus dE by dt is the amount of energy that's being radiated, and then that is proportional to E squared. E squared for a large gamma, so it would be obviously equal to 1. And this, the reason this is helpful as a mechanism for working out the properties of a source that you can't get your hands on is that that E squared term means that the higher energy electrons radiate their energy away first. So this process doesn't just move the entire population down in energy, the higher end of the population preferentially loses its energy. So before we discuss this applies to the whole spectrum, let's just define a cooling time and see how that works. Right, so let's say for electrons with some energy E, I'll define tau just to be the instantaneous value of E over dE by dt. And then substituting in what we had before, that means that goes as E over 4 over 3 sigma t, speed of light, magnetic energy density, U mag, E over c squared, and gamma squared. And just to be explicit about the magnetic field, because that's something we'll come back to in a minute, we get 4 over 3 sigma t c b squared over 2 v naught and then gamma squared. So okay, so for large gamma, we set b obviously equal to 1. Now, that's a timescale which will give you the first order term in any. That will give you the first order term in any diffusion equation solution that you make out of this. But what I want to do for simplicity's sake is just to make the point that after, so if you take a synchrotron population, take a region with synchrotron and plasma, you accelerate that and start plot. And then you come back sometime like after 10 mega years or 100 mega years. What you'll find is that any electron energy whose cooling time is less than that age, it won't be there in the population anymore. So if I start our population like so, so here's E and N of E. Right, and this population can go up to arbitrarily high energies. So it may be the case that this goes up to some energy that corresponds to a very, very large DARA radius when the initial acceleration was done. Then you let your plasma sit there, and characteristically what we do is we say, okay, this is in the big lobes, this big cigar-shaped cocoon of a radio source. And then if we come back at some time later, there'll be some, still again this is going to be against E, there will be some cutoff, very sharp cutoff in the population at the energy that's defined by that particular timescale. Now think about this a little bit. What's happening is that it's not to say that these electrons have disappeared from the population completely. Right? The electrons are still there, but if you started out with some electron emitting, say, at a radio frequency of 10 gigahertz. That electron radiates away, and if you put a flag on that electron and you come back to the population a long time later, you'll find that that particular electron has now got a lower energy, so it's radiating at a much lower radial frequency. And so because this timescale corresponds to that time it takes to radiate away a particular amount of energy, then the population as a whole won't have any emission coming from electrons with energies larger than this left over in it. Okay? So it's not just the case that the whole emission split shifts to the left. Some of these electrons are moving down to lower energies. And the other thing that's folded into this is because this, in reality, because this spectrum is so steep, typically e to the minus 2, then the individual electrons that you see here do not make a significant increase to the emission that's coming out at low frequencies. And to make that point a little bit clearer, I'll just do it on a linear scale. N of E is proportional to e to the minus 2. Okay, what's happened is that was the original population, and now those electrons have disappeared. And yet the individual electrons are still in the population here, but the difference that they make to the emission coming from the lower energies is small enough to be negligible in these circumstances when you're looking at an actual radio source with an e to the minus 2 spectrum. Right? In reality, if you did this in detail, yes, you put in your diffusion equation and there will be a little bump here as you conserve electron number. But it's so small compared to the large rest of the mass of the bulk of the electron population that it's never observable in practice. What you can see, however, is the fact that you do get a characteristic cutoff. Right, so population of electrons that was accelerated to high energies at some time t equals 0 in the past, and then allowed to radiate will have a cutoff in the synchrotron spectrum. At a frequency so gamma squared, electron charge, magnetic field strength over 2 pi, and electron mass. So where that gamma squared, that gamma, that's the Lorentz factor of the highest energy remaining electrons. And that's why you get this idea of, as it's called, spectral aging. Okay, and now we can go to some more pretty picture stuff with some more phenomenological material for the last chunk of the lecture. Okay, There's mine. Oh yeah, sorry, I noticed that as well. That is the PDF thing, tau is an exclamation mark. PDF obviously doesn't speak Greek. That's a tau. Okay, and this is what it looks like in practice. So what we're seeing in this plot is this is a zoom in to the high frequency end of a particular source. So we've got frequency here in gigahertz. So 0.1, 100 megahertz, 1 gigahertz, 10 gigahertz, up to getting towards about 20 here. And what you're looking at here is there's a low frequency tail coming in with our standard injection, and then it breaks. In log space, it breaks very, very quickly. And in this case, the idea is that it's seen to break, and the best bit value for the break frequency is 4.5 gigahertz. The idea here is that there are no electrons left in the population that are radiating at any significant frequency higher than 4.5 gigahertz. So that's our overall spectral shape decided. You've got a rising spectrum at low frequencies where it's optically thick. Then over the broad, optically thin region, it starts out with a freshly injected population, shallow as you get to about 0.5, and it starts to steepen. And then the break frequency here, as an individual population gets older and older, this high frequency cutoff cools down and down and down and down in frequency as the population gets older. Right? And this is how it's done in practice. This slide and the next one are some maps of an individual quasar at different radio frequencies. So this is 1.4 gigahertz. So black hole type object in the center, and then these are the ends of the jets. See here, relatively low resolution. These are the ends of the jets where the jet hits the intergalactic medium and is slowed down. We move up now to 5 gigahertz, and what you can see just straight away by eye, because the contours have been chosen to do so, you see that the emission at the center is starting to get fainter. And then as you move up to higher frequency, still now we're up at 15 gigahertz, the very tips of the jets are still visible as being bright, but near the center of the source, the emission has almost completely disappeared. What's going on in this case is that now if you just do it looking at the spectrum at each point, rather than just looking at contour plots, what I've done on the graph here at the bottom right, at least I've taken the graph from the paper with which this is originally presented. And then you'll see each of these strips, we integrate the full flux of the object on each of those strips. And you see near the hotspot at the end, the break happens at quite high frequency. And as you move backwards, the break happens at progressively lower and lower and lower frequencies. So what that's saying is that if all the fluid dynamics is relatively simple, and if the magnetic field across the source is uniform, and these things have got a lot of assumptions in them, but the point about them is that you can have test cases where nature's, certainly the natural circumstances of a particular object all play in the right direction. What's happening here is that the plasma down here near the host galaxy is significantly older than the plasma up here at the end of the jet. What we believe is happening is that on a long time scale, the jet is burrowing its way out into the intergalactic medium, and it leaves behind it the plasma that's just recently flown up along the jet. So a way to picture this is like taking fire hose or something like that, a high pressure water hose, and blasting that into a thick pile of sand or something similar. But gradually you'll back away and you'll eat away at the sand, but the water that you leave behind in a puddle on the ground, the one closest to you will have been on the ground longest by the time you've eaten away into this pile of sand. That's what we're seeing here. We're seeing the older plasma is at the center, and then relatively younger at the edges. And I've left this as an exercise for the reader. This is a question on the problem set to deal with this. So you're given a source, you're given this cutoff frequency at some point. From the cutoff frequency, you can infer what the energy of the underlying electrons are. And then if you know that electrons at that energy are still in the population, you can find out from the time scale what the time is since they were first accelerated. If they're the largest, if they're the highest energy electrons still present, they must be the ones that are just about to fade away below the cutoff frequency. and that gives you the time since that plasma was originally accelerated. Now, just to give you a couple of quick caveats on this, one thing is, yeah, you need to make sure that you've got nice, simple fluid dynamics. Okay, so here's a couple of examples of sources where on the left, definitely something complicated is happening here. It's probably the case on an object like this on the left. There's a hot spot at the end of the jet, and the fluid is flowing up the jet here, and it's probably actually streaming down inside the lobe and streaming outside it. So there's internal bulk motions of the fluid. Now, if that's going on, you can say, right, I won't use this sort of object to do this analysis. Okay, what you're doing is you're going through the zoo of radio sources that make it given you, and you pick the ones where the fluid dynamics works nice and cleanly. So something on the right-hand side here, from the image of the object, you can see that the jet is just going out in a nice steady fashion. Now, in practice, maybe it's maybe it's 1/3 of objects that you can do this for. But the point about it is the analysis comes out as being reasonably self-consistent. And what we find is the numbers here are quite interesting, and they will have a big impact when in a couple of lectures' time we talk about the global history of growth of black holes over the course of the life of the universe. Typically, the jet itself goes out into the intergalactic medium at a speed that's maybe only about 1 to a few percent of the speed of light. The bulk speed of the plasma coming up the jet is very high. We might have a launch time of 10 or 30, and I'll discuss the evidence for that in a couple of lectures' time as well. But the speed at which the ends of the source propagate into the intergalactic medium is much, much slower. Now, the largest sources here, the oldest ones that we find, they seem to be something like maybe 10 to the 8 years old. And that is a small fraction of Hubble time. That's a small fraction of the Hubble time. So what we conclude from this is certainly for the extremely luminous sources that seem to do this, is that sort of event, if it happens in any particular sort of galaxy, that can only be a short fraction of the galaxy's lifetime. So either this is a sort of event which happens once in a while in a very, very small fraction of galaxies, or it happens in most galaxies, but it happens maybe at most once or twice during the history of the universe. And this is something that we end up folding into our picture of why almost all massive galaxies today end up having a quiescent black hole in the center of them. Okay, now so it's a little sort of digression on this, but it remains one of the very, very interesting topics in galaxy evolution right now. Is that probably you can infer. I'm showing you the prettiest and most simple, and also the most luminous objects in these sort of categories. And one catch that comes into this is that, looking at these, you're selecting the very most luminous and the very simplest straight jet type objects. And actually, the vast majority of sources, when you look at them, especially with the present generation of radio telescopes, where we can get to very, very low luminosity sources out of large distance, is rather than something like on the left, where you've got a nice, clean, very high luminosity jet, terminates in the jet socket, and then you have a sort of cigar-shaped structure of plasma. Actually, an awful lot of galaxies have got a much lower luminosity object. So see, the blue here is the starlight, and the red is the radio imaging plasma. And in these sorts of objects, the radio jets do start off close to the black hole, and they start out fairly well dominated. But these jets are much lower luminosity, and they've got much lower jet power and slower jet speeds. So they start to become unstable. And it's pretty much like you can consider that this is a spherical gravitational potential well, so every direction is up. This is much more like chimney smoke than becoming unstable. It's the colder, less dense, certainly in this case, it's probably that these people will be close to isothermal atmospheres, but the less dense material. So as the Mach contrast with the jet changes very dramatically, so it's a low power jet gets in the transonic region very quickly, then it becomes unstable. And just to use the jargon here is that these are called Panarov-Riley type 1 and type 2 objects. Of the people who first named them, I just want to name check these two in particular, two pretty giant figures in radio astronomy. Julia is well known because I'm sure you'll be aware that there still is a lot of controversy about Eddington's measurement of the deflection of the sun in the Friendship eclipse. expedition on. You look at these photographic plates, and you're looking for a collection of something like half an hour second compared to the Newtonian bricks, which is half the Einsteinian bricks. They're still rosy. So, and Dewey was the person in the late 1960s who first did it. I said, why we can do this in the day, we don't need a silver eclipse if you do it with quasars. And so the first high-resolution radio telescopes in the 60s, that was the first deflection measurement with no ambiguity about the positions of the background objects in that case. And Bernie Klameroff now, Bernie recently retired, but he was a grad student at the same time that Julie was a postdoc in the radio astronomy group in Cambridge in the 70s. And then he went on to be a huge figure in South Africa in astronomy, and was science advisor in the Mandela Movement, and then was director of the SKA. And so when you see FR, basically these people have become so sufficiently famous that you can say FR1, FR2, you don't need to give them a citation anymore. Everybody just knows, probably in 1974, run out of getting citations. And which in modern science, where universities are ranked by the citations that all the papers get, is a bit of an irony when you're so famous you don't get citations. How is that accounted for in the quantitative ways that universities are measured nowadays? Anyway, what I'll just round off with is, this complicates the picture. And what we don't know in particular, because this aging technique relies on the fact that the plasma is dumped and then left alone and dumped and then left alone and dumped and then left alone as a very high power jet goes out. It means that we've got much, much less certainty about what the lifetime of these very, very low luminosity sources is. And so, for example, it might be the case that a very, very low luminosity radio source exists in almost all massive galaxies. And if you're really up to speed on your popular scientific high energy astronomy, like the Fermi bubbles, in recent years it's become clear that the first mission camera satellite that was 10 years ago, that even the Milky Way has got little high energy lobes of emission. We can only just about see them because we're inside, and even the Milky Way has got little high energy lobes. Now we don't know whether those are because the Milky Way black hole has very, very weak jet that flickers on and off occasionally. It's certainly not lit up right now. It may be that it's star formation causing these outflows at low luminosities, but there's definitely, as our technology gets better and we're able to detect more and more low power sources, it's clear that there's a large fraction of galaxies that have got some level of activity, and this is probably contributing to the supermassive black holes that lie in any galaxy in the modern universe, being one method or not. Milky Way has got 3 million solar black hole in the center, which is not active right now, but it may be the case, on the remnant bubbles that we see. It was active as recently as a couple of million years ago. So there's an awful lot of stuff lying just below the surface. And definitely, if you get into this game now, if you think you're doing PhD in this sort of area, there's an awful lot to be discovered as the next generation of radio telescopes. The picture outside, that's just what I got there, which shows you when a meerkat starts producing the surveys in the next year or so. Awful lot of stuff going on in this area. Okay, right, I will stop there, and then next time we'll start with completion.